So the first guess was too big. And we came up with a ratio that was 10 times too big. And so the next guess that was suggested is a guess that's 10 times smaller. And so it's tricky because sometimes these are nonlinear ratios because we have squared terms and other stuff. But we can give this a go and see what the ratio comes out to. And so I'm just going to go ahead and multiply that out here. It's going to be 4 times 0.003 squared times 1.103 divided by, so that's 6.094 squared divided by 0.047. And now it's coming out, assuming I did the calculation correctly, 0.00892. This door should have been unlocked. So it's too small. So we're going to have to do another guess. And you can see, this, even though the ratio is 10 times smaller, so if you make x 10 times smaller, if it were linear, that is, there are no exponential terms like squared or cube or whatever, then it would have worked, but it's a bit more tricky, so we'll just have to guess something else. So what's your next guess going to be? Somebody give me, unless, did other people get this number? Yeah, you want to double check the calculation. So I'm going to guess x is equal to, we still want to keep it to 1 sig fig for right now. So we want to minimize the amount of button pushing we have to do to the calculator. And so what would you suggest? Remember the range for the x has to be between what and what? The range for x has to be between 0, it's got to be greater than, it could equal, actually it can't equal really, but let me get rid of that. It's got to be greater than 0, because if we put in 0 there, then there's no way the ratio is going to equal 1.4, and less than 0.5. Or not 0.5, 0.05, sorry. All right, so give me another guess. Okay, that sounds good. 0.02. So if we do 0.02, then just punch it in the calculator again. 4 times 0.02 squared times 0.08. Oh, no, not 0.08, 0.102. Or not 0.102, 0.12. Let me see if I got that right. 0.1 times 0.02, 0.12. divided by, okay, that's going to be 0.04. So that's going to be 0.06 squared divided by 0.06 squared divided by 0.03. See what we get. And so this gives us a ratio of 1.777. What was the ratio supposed to be? Let's see. The ratio is supposed to be 1.48. That's what it's supposed to equal. And so we're close. Just slightly big. And so what would your next guess be? Since we're very close, I wouldn't go to 0.01. 0.01 is probably going to throw us too far out. You see that? And so what would you try next? My guess would be I'd just try an x equals 0.019. Something like that. Now, if it's 0.019, then it's more difficult to do in my head, some of the calculations, but I'll try. 4 times 0.019 squared times, this one's easy, 0.119. Do that in my head. Divided by, let's see, 0.1 minus 0.019 is 0.081. Oh, actually, no. That's 2 times 0.019. 2 times 0.019 is 0.038. 0.1 minus 0.038 would be 0.062. So 0.062 squared. Or you just use parentheses, it's fine. Divided by 0.05 minus 0.019 would be 0.031. And I get 1.442. So, again, I'm close, but I'm a little bit small now. I need to bring it up to 1.48. So what would your next guess here be? I'd say, is it closer to 0.02 or is it 0.020? Is it closer to 20 or 19? It looks like it's closer to 19, doesn't it? And so actually it's just very, very close to 19. So maybe what I'm going to do is I'm going to go closer to 19 than 20. So I'm going to go 19, what? 5? 19.5 would be kind of midway in between here, because if we're at 19.0 and we go to 20.0, 19.5 is right in the center. And I think it's closer to 19 than it is to 20. This would be 20 here, even though, you know, I didn't punch it. And so I think 5 is just a little too far away from 19. I would do something very close to 19, like 19. I would do 19.1. You know, we're really close. I mean, 144 versus 148. We're really close. And so I'm going to do 0.0191. So this one I'm going to just punch in my calculator. So 4 times 0.0191 squared times, I'll just do the parentheses here. Oh, actually, I don't need the parentheses for this. 0.1191. 0.1191 divided by, I'll do the parentheses for this. I'm going to do 0.1 minus 2 times 0.0191 0.0191 close parentheses squared divided by parentheses, we'll just do it, 0.05 minus 0.0191 close parentheses equals. And I get an answer 1.472. Now we're getting awfully close, right? But we're still a little bit small. I want 148. We're at 147. And so when I think about it, I just need it a little bit bigger. And so my next guess should be what? I'm sorry? 192? Okay, we could try 192. Let's see what that gives us. So at 192, I'll do 4 times 0.0192 squared, okay, times 0.1192 divided by, I'm going to just do this, parentheses, 0.1 minus 2 times 0.0192 quantity squared divided by 0.05 minus 0.0192. And that gave me 1.503. So it's too big now. And so what would your next guess here be? Yeah, so we look, is it closer to 191 or 192? 191. So I'm going to go 191.3. That sounds reasonable. Let's go with 191.3 and see what happens here. Okay, so 0.01913. So going back to the equation, 4 times 0.01913 squared times 0.11913 divided by parentheses 0.1 minus 2 times 0.01913 close parentheses squared divided by 0.05 minus 0.01913. Oops, I forgot the parentheses. Delete that. So I got 1481. Should we try to get 1480? No, because of this, you know, we just needed to round to this. I'm only doing 3 sig figs here because it was like a 147, or what was it? No, 2 148s and a 149. So it's slightly bigger than 148, the average that we used. And so this is enough. If we can get it to agree to the correct number of sig figs, then we're done. sig figs SF. And therefore x is 0.01913. I need to insert some more pages, but Word makes it very difficult to insert more pages. Here, when you do drawings. Actually, maybe I shouldn't. And so this was from today here, 226. I tried to post the notes before, but since Word crashes so much, then I switched to Excel. Then sometimes I've had to switch to PowerPoint. I stopped doing it because it gets too mixed up, complicated. All right, so we determined that our x came out to 0.01913. That was our best value. Well, we could try more. You know, maybe 1912 might have been better. Maybe 1912 could have given us a 0 there, but as long as we're matching to the same number of sig figs, then let's just stop here. You know, so when we say best, it's the best compromise between time and accuracy. All right, now what we're going to do is we're going to go back to the equation which it was here. So we have the copper 2 plus oxidizing the tin 2. Copper is reduced to copper plus 1, and tin 2 is oxidized to tin 4. And our initial values for this were 0.100 moles, 0.050 moles, and then 0 moles. And what did we have here? 0.100 moles, is that correct? Yeah. And then our change here is going to be minus 2x minus x plus 2x plus x moles. And that change, we're going to use this x value here. So we're going to go ahead and write that in. So 2 times 1913 is what? I don't want to figure it out. 3826. So this is going to be minus 0.03826 moles. And half of that divided by 2. Oh, that's no. I got to double it. Sorry. This is incorrect. I need to double that. Not divided by 2 times 2, 7652. So this is actually minus 0.07652 moles. And then over here, 0.05 minus x would be minus point. Oh, what am I doing? Sorry, I already doubled it. Third error. Usually we make errors in our lab notebook. Yeah. When we make an error in the lab notebook, you're supposed to leave it legible. So what we typically do is we just draw 1 line or 2 lines through it. So you can still see the error here. So I see my errors. This is good lab technique. What you don't want to do is you don't want to white it out. You know, if I white this out, you know, in our lab notebook we're supposed to use ink because ink is more permanent. That's just for the raw data. For calculations we could use pencil. So if I use pencil, I'd just erase it. You know. But with the raw data, I would use ink. But if I used ink here, I would just cross it out like this. I wouldn't put whiteout over it or correction tape because if the whiteout, you know, the liquid paper breaks off, you know, after it dries, then you don't know if that was a mistake or not. Or if the correction tape peels off or something like that, you know, with age. Some experiments, when I was doing experiments, you know, some of these, like I had multiple things going on. And so some projects, little projects here I was working on for multiple years, you know, and so I'd have to go back like 2 years, 3 years or something and look at what I did. You know. Pencil actually fades quite fast. And so it might be fine, whiteout and correction tape initially, but you know, after years, maybe 5 years or something, you go back and look at it, it's not so good. And so the original one was correct. I forgot, I'd already doubled it here. So 0.03826. And then this is going to be minus 0.01913. And this is going to be plus 0.03826 moles. And this is going to be plus 0.01913 moles here. So by the end of this, what do we have? By the end of this is 0.1 minus this, 0.03826. So I'll just use my calculator. I'm too lazy to think about this too much. 6174. And then this one, 0.03. Actually, I could probably do this one. 0.87. This one's easy. I could do this in my head. 3.826 moles. And this one's easy. I could do this one. In my head. So we're only allowed 3 decimal places. So really I'm carrying extra digits here that aren't allowed. But the reason I always carry extra digits that I'm not allowed in Chem 1B because I want to do a double check. So if I'm only allowed 3 decimal places, then, oops, what happened there? Let's try that again. Then I need to drop the 7.4, right? Those aren't allowed. In 3 decimal places here, I need to drop the 8.7. Those aren't allowed here. I need to drop the 2.6 and the 1.3. Those are extra sig figs, extra digits that aren't allowed here. And the reason I always carry extra digits is because I want to check the ratio. This is one way to check your calculation. Remember, this gave us a ratio of 1.48, a little bit more than 1.48. And so what I'm going to do is I'm going to go ahead and check the ratio to make sure it's correct. And when we check the ratio, I don't want rounding error. You know, rounding error can significantly alter it. And so to minimize rounding error, I carry extra digits. That way, you know this. You can eliminate the possibility of rounding error. If you carry extra digits, then you go, my number is off. But is your number off because you made an error in the calculation? Or is your number off because of rounding error? Those are two things that can contribute to errors. And so these extra digits here are to eliminate one of those potential sources of error, or to minimize rounding error. Therefore, if our ratio comes way off, we know it's not due to rounding error. We know the ratio is off because of a calculation error. If it's a calculation error, we go back and double check all our calculations. If it's a rounding error, I don't go back. I mean, if it's within rounding, I just say it's good, usually. And so I'm going to check the ratio here, and that is we take the product copper, 0.03826, squared, times the tin 4, which is 0.0. This didn't come out right.
It's 0.03826.
Yeah, 0.03826. The tin actually is 0.1, sorry, because we started off with a lot of tin to begin with. Is it correct? And so the tin is actually 0.11913. All the units cancel, so I have mole squared here times mole will give me mole cubed. Do you see that? And so I have moles cubed on the top. And then what do I have on the bottom? Well, I have on the bottom 0.06174 squared times 0.03087. And this would be moles cubed here. So the moles cubed cancel the moles cubed. So chemists are sticklers for making sure the proper units are on there. So 0.03826 squared times 0.011913 divided by, oops, I screwed that up already here, 0.11913 divided by 0.06174 squared divided by 0.03087. And what do we get? We get 1.481. So the ratio checks out. So the ratio checks out. So it looks good. The last thing we want to do is we want to verify this experimentally, right? And finally, experimental verification. Actually, this is not really the final step. I should say experimental verification checks out too. What's most important is it agrees with experiment. And so concentrations, these concentrations agree with experimental observations. Okay, so it looks good. You know, we have a pattern. We have a consistent pattern. We have a consistent mathematical pattern. Do you know what we call that? We call that law. And this one is an empirical law. Do you know what empirical means? Based on observation. Versus what? Yeah, good. Theoretical. And so our law is based on observations here. And so what is our law? Our law, I'm going to make this new law here. I'm going to take a generic reaction, AA plus BB, etc. goes to GG plus HH, etc. You know, dot, dot, dot. And so what we're going to get for this new law is that the ratio is equal to a constant, which is equal to the moles of G times the moles of H. Now G is going to be raised to the coefficient G power, and H is going to be raised to the coefficient H power, divided by the moles of A raised to the little a times the moles of B raised to the little b. And this is, you know, the final number of moles. And so I'm going to say moles of G at the end of reaction, moles of H at the end of the reaction. At the beginning it doesn't have to fit this ratio, but at the end it better fit this ratio. And so that's why I'm going to say E there for the end. And what I said about laws, you know, we expect minimal exceptions to the law. Otherwise, I'd call it like a rule. This law turns out to work well, you know, for other reactions. So we should test the law and see how it works. We should test the law on other reactions. So let me insert some pages here. I forgot to do that. The law works if the moles cancel between the numerator and denominator. Unfortunately, when people tested it on other reactions, it fails if moles do not cancel. And so what do I mean by that? an example is if I had a reaction that was, let's say, A plus 2B yields 2C. Then what I'm going to have in this particular scenario is I'm going to have moles of C at the end squared divided by the moles of A to the first at the end and the moles of B at the end squared. And so when I look at the units are going to come out to this. The units come out moles squared on the top divided by moles cubed on the bottom, which is going to give me 1 over moles as my unit. What is an inverse mole? Well, when we have reactions like this, then the ratio fails. If the ratio fails, is the law still valid? No. The law just happened to work for that one reaction and others that are similar to this. So this pattern failed. Actually, the pattern held okay for that. The pattern and law failed for these types of reactions. So one, you could just use this pattern for only one type of reaction, or two, we got to look for a new pattern that's consistent for all of them. And so a search for a new pattern began. So what would you try next? You can move these. Any ideas? So this is a lot of work, obviously. It's not so easy to find new patterns, is it? But after searching, a new pattern was found. And this new pattern was determined to be this. So if I take any reaction, AA plus BB, and it need not cancel or whatever, plus CC plus dot dot dot. This is in equilibrium with the products GG plus HH plus dot dot dot, where we have the coefficients in lowercase and the substances of the reactants products in uppercase here. And this is for aqueous, sorry. Aqueous. The new pattern came out like this. If we take the G, the square brackets, what do the square brackets mean? Yeah, concentration. Molar concentration. So rather than using the amounts in moles, they use the concentration in molarity. And from this, they got this to be a constant, which we call K. K is the equilibrium constant. And this would be the equilibrium law here. And through testing, it works well. For dilute solutions. Of lower charge. But if you have higher charge species, and as the concentration goes up, then it deviates. So the higher the concentration and the higher the charge on the ions, the more it fails. Have you seen something like that before? Testing works well for dilute solutions of lower charge, which we call ideal solutions. These are called ideal solutions. Ideal solutions behave in a certain way, but unfortunately real solutions sometimes deviate from ideal behavior. And so we might think of something as being, 1 mole or 1 molal. You guys know molality? Let's say you might think of something as being 1 molal, but sometimes its concentration can behave a lot less. I remember this problem. I was a teaching assistant at UCSB, and I remember the professor gave a test. So this will be side. And he was talking about, I think it was benzoic acid, or maybe it was acetic acid. No, I think it was benzoic acid, something like that. And the problem with it is this. The problem with this is that these benzoic acids, in an ideal solution, there'd be a lot of waters around here. And benzoic acid would be your solute, and the solute molecule, there's a benzene right there, it's just floating around in solution. But what can happen is this. What happens is it behaves like half as concentrated as it really is. And the reason it behaves like that is because of something called dimerization here. It's like, say, one benzoic acid passes by another. Did you guys review chapter 14? Does anybody recall what I asked you to look at from chapter 14? Just one page of chapter 14 I asked you to review. Does anybody remember what the one page from chapter 4? I don't want you to review it the night before the test. You know, if you review it before the test, it would be better in case there are questions that come up. But since nobody had any questions, I assumed everybody understood it. What was it? Or, you know, you could just cross your fingers and hope it doesn't come on the test. You know, that's another alternative. A lot of people do that. A lot of people say, that's too much to study. That one page is way too much. Maybe it is way too much, you know, reading. Take me like 20 minutes or something to read it. Anybody read it? It takes you 20 minutes to read it, but it takes you a lot longer to understand it because it's kind of weird, complicated stuff. You know, and sometimes it doesn't take that long to read it because there's not a lot of math. You know, some of the other stuff, one page, sometimes it takes you so long to read, like one chapter. Sometimes I could spend 1 hour on one page because there's so many calculations on it. And trying to figure out all the calculations because oftentimes what they do is skip steps. And they skip steps so you want to see what all the intermediate steps were. So you can make it more systematic. But sometimes they jump from one thing to another and you go, how did they jump from there to there? And then all of a sudden that one page starts taking a lot of time. I think I even gave the page number for that. Pearson. Or maybe it's my imagination. Did I mention this? I thought I did, but my memory and mind is fading. In my table of contents. Oh, here it is. You have to you'll want to do this like sooner, especially like in like hyper competitive places. Like UCLA is kind of hyper competitive, especially for pre-med. A lot of people want to get the high score. It probably begins before this. But It's actually more, maybe more than one page. I don't know. Table 14.4 illustrates it pretty well. This is deviations from ideal behavior. If I had sodium chloride and I had 1 mole sodium chloride, it should split up into 2 particles, a sodium ion and a chloride ion. And that we call ideal. And so, ideal behavior of sodium chloride, when you dissolve sodium chloride is a strong electrolyte. What do strong electrolytes do? They dissociate 100%. However, as the concentration increases, it starts to deviate from ideal behavior. And so ideal behavior would be quite dilute. And then what we have here is an effective concentration of 181. And so if it's supposed to be 2, that's like 90%. That means about 10% of the ions, what happened to them? What happened to those 10% of ions or whatever is they kind of pair up. And they form something called ion pairs. Ion pairs, well, we look at that table. There's a figure in this book. Hopefully they have it here. Let's see, they have the figure. Yeah, or ion clusters. So they don't behave independently. Let's say if you have a pair here, then they aren't independent ions anymore. They're a couple. And if they're a couple, they're going to decrease the effective concentration. Or an ion cluster here. Now these couples and clusters are going to form at higher concentrations, or if there's higher charge on the ions. If there's higher charge on the ions, then that becomes even worse. And so this is this kind of ion-ion interaction. Like this. And so you can see, just quickly, what we do is we look for a pattern. The pattern is the more concentrated, the more it deviates. The other pattern is the higher the charge on the ions, the more it deviates. So magnesium sulfate should break up into 2. It effectively breaks up into 1, so everything's paired. Does that make sense? Here. And therefore, we have kind of 2 concentrations that we deal with. One concentration, 2 concentrations that we deal with. One concentration is called the stoichiometric concentration. Here. The other concentration is called the effective concentration, or aka the activity. Now you remind me, did I ask for people to review activity, or did I forget to ask people to review for activity? Does anybody remember me talking about activity? Searching the book? Okay, if I forgot, now is the time. Go back. It's only a page and a half to review from chapter 14. Review activity for me. Activities, effective concentration. Activities are dimensionless. They have no units. And so what happens here is that the benzenes don't act independently. What happens is the benzenes kind of get caught with one another and they stick together because of these hydrogen bonds here. It's like DNA kind of thing. And this is what we call a dimer. You know. And so that's going to lower the effective concentration considerably. And so we might have 1 mole, it behaves like 0.05 mole, or I mean not 0.05, 0.5 mole, half, you know, is this. But we could have also ion-ion pairs, you know.
Which section did you want us to review? 13?
It's near the end. I did a search. I usually just search it, activity, but what page number is this? I don't have the PDF version. They have this weird version of the book for me. But it's 14.9. review that one section of the book. Because it turns out our pattern fails. But this is nothing new because other patterns have failed. Remember the ideal gas law? The ideal gas law deviates low temperatures and high pressures, right? And so it fails. The ideal gas law fails too. And so what we need to do is we need to do it for real solutions, or for all solutions. And so finally we come up with a pattern. So a new pattern. And K is going to be the activity of G raised to the G power, activity of H raised to the H power, dot, 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 divided by the activity of A raised to A power, activity of B raised to the B power. So we should use activities. Must use effective concentrations. But, well, especially under what conditions? You must use effective concentrations, especially under what conditions? You know, do you guys remember the van der Waals equation for real gases? PV equals nRT doesn't work all the time. Sometimes PV equals nRT fails miserably. So we use something called the van der Waals or the Virial. They're different equations that try to describe real gases. It's like P plus, what was it, N squared V over A squared. Actually, I don't have it memorized. I rarely use it. I'm sorry?
I have it here.
Oh, okay. All right. Well, let me just show in the book. Is it from our book? Why can't I search the textbook? Do you remember 6.9? Probably didn't talk about it in 6.9 non-ideal real gases. We can get a gauge about how much deviation we get from ideal behavior. You know, if a gas behaves ideally, then it conforms to the ideal gas law. But some gases deviate. Some of these gases deviate so small. I mean, 1.005 versus 1, or 0.998 versus 1. Those are such small deviations, it's close enough. But other gases have more significant deviations from ideal behavior. So, for example, SF6. If you were to do SF6, this significant deviation from ideal behavior. SO2, significant deviation from ideal behavior. And therefore, you shouldn't use the ideal gas law for SF6 or SO2 because those deviate quite a lot from ideal behavior. And therefore, you should use another equation. This other equation we could use for all the gases, ideal or non-ideal. This is showing the deviations. There are two types of deviations from ideal behavior. One is intermolecular attractions. Two is the volume of the particle. Those are the two deviations from ideal behavior. And therefore, we modify the ideal gas law. So this is an ad hoc modification to the ideal gas law. And this is called the van der Waals equation here. And so it's P plus n squared A over B squared. That's right. B minus MB is equal. So we correct the pressure, correct the volume. And then A and B are essentially A is for the intermolecular attractions. The bigger the A is, the stronger the intermolecular attractions and the bigger the deviation we have. And so N is for intermolecular attractions and B is for the volume of the particles. The bigger the particles are, the less actual empty space volume we have. And so we have to make corrections there. But do you use the van der Waals equation for every gas calculation? We should, but we know that as long as the pressure is fairly low and the temperature is fairly high, like room temperature or higher, then gases behave close to ideal, right? But if there's strong intermolecular attractions, like water, water has strong intermolecular attractions because of hydrogen bonding interactions, right? And that's going to deviate more from ideal behavior. And so water doesn't behave ideally, as a gas. Let's say I wanted to calculate the pressure of water gas at 0 degrees C. Am I going to get a good accurate calculation using the ideal gas law? No, at 0 degrees C, I'm going to have a chunk of ice. It's not even a gas. And so obviously that's going to deviate dramatically from the ideal gas law. So the point of all this is this. This holds for everything. However, activities are beyond the scope of Chem 1B. Calculating activities is beyond. You'd have to go to the next class to do this. But calculating activities is beyond the scope of Chem 1B. So we're going to do the exact same thing we did for gases. We're just going to use the ideal gas law for all gases and realize that we could have a big error if the gas is not very ideal. And the same thing here. We could have a big error if we're dealing with a solution that's not very ideal. Okay. So what we're going to say is that the activity is of a solution is close to the molar concentration, more or less. More if it's ideal, less if it's not so ideal. And we're going to go on because we're going to need this later. This holds for everything. If we have an activity of a gas, the activity of gas is going to be close to the partial pressure of the gas, more or less, depending, how ideal is that gas. If that gas is quite ideal, then this is good. The activity of a solid is equal to, or just about equal to 1. It's not defined, but is 1. The activity of a liquid we'll just take as 1, 2. And so solids and liquids have unit activity. So now we're going to have this new law. If we have all solutions or all gases, Then K is equal to the concentration of G raised to little g, concentration of H raised to little h, etc., divided by A to little a, B to little b, etc. This we call Kc. And then we have something called Kp. Kp is going to be the partial pressure of G raised to little g, partial pressure of H raised to little h, over partial pressure of A raised to little a, partial pressure of B raised to little b. If we have heterogeneous states, then we're going to mix concentrations, pressures, and activities equal to 1. And so let's take this one here as an example. Calcium carbonate solid plus 2 HCl's yields calcium chloride aqueous plus H2O liquid plus CO2 gas. So K for this is going to equal the concentration of calcium chloride times 1 for liquid water times the partial pressure of CO2. These are all raised to the first power, divided by 1 for calcium carbonate times the HCl concentration squared. And so we have a mix of different things. And so this is like, this is okay, now we have kind of the van der Waals equation with activities, but we're not really going to use that. We're just going to use the ideal and assume everything's close enough to ideal. And hopefully it doesn't deviate too much from ideal. All right, I'm going to stop here. Any questions on this? Stop here, and then we're going to do check-in next. And then after check-in, we're going to do a worksheet, quiz/quiz. This worksheet quiz is going to contain some questions about chemical reactions, but the test next week is not going to have chemical reactions. The test next week is just going to have complexes. And so this worksheet is going to have some chemical reaction stuff to get you thinking about chemical reactions, and some complex stuff like nomenclature and ligands and that kind of thing. And this worksheet you could work with others if you want. It's fine. I'll stop.